The cylinder head temperature gauge climbed past the red line, and Lieutenant Tadashi Nakajima knew his Nakajima Ki-84 Hayate was dying. It was the morning of February 15th, 1945, somewhere over the Philippine Sea, and the most advanced fighter aircraft the Imperial Japanese Army Air Force had ever produced was being run down like prey. Behind him, gaining with an almost contemptuous ease, came the machine that would end his war, a Republic P-47 Newtons Thunderbolt, its massive radial engine pulling the 7-ton fighter through the sky as if weight meant nothing. Nakajima had done everything right. He had used his aircraft's superior maneuverability, its lighter wing loading, its ability to turn inside the American. None of it mattered. Every time he escaped one attack, the Thunderbolt simply climbed away, regained energy, and dove again. The American pilot was not particularly skilled. He did not need to be. His engine produced power that Nakajima's aircraft could not match, could not answer, could not escape. When the 50 caliber rounds finally found his fuel tank, Nakajima bailed out over open water. He would spend 3 days adrift before a Japanese patrol boat found him, delirious and half dead from exposure. But even in his delirium, one thought consumed him: how could an engine that large, powering an aircraft that heavy, produce that much power? The Hayate's Nakajima Homare engine was Japan's finest, the culmination of a decade of development. It produced 1900 horsepower on a good day, when the spark plugs did not foul and the supercharger did not fail. Yet the American engine had simply overwhelmed it. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The answer to Nakajima's question would not come until months later, in a research laboratory outside Tokyo, when Japanese engineers finally understood what they were fighting against. It was not simply a matter of displacement or compression ratios or supercharger design. The Americans had changed the rules entirely. They had found a way to make gasoline burn hotter, longer, and more completely than anything the Japanese industry could produce. The secret was a chemical additive called tetraethyl lead, blended into aviation fuel at concentrations that Japanese refineries could not match and Japanese engines could not survive. With it, the Americans had unlocked power outputs that seemed to violate the laws of thermodynamics. The P-47's Pratt & Whitney R2800 double wasp did not merely produce more horsepower than Japanese engines in certain configurations, with water injection and high boost settings. It produced 2800 horsepower, nearly 50% more than the best Japan could field. This is the story of that discovery, of the Japanese engineers who slowly pieced together the terrible truth about why they were losing the air war. It is not a story of heroic dogfights or legendary aces. It is a story about chemistry, about industrial capacity, about the crushing mathematics of a war that was decided in refineries and laboratories long before it was decided in the sky. It is the story of men who built the best aircraft their nation could produce, only to watch them fall from the sky because they could not be fed the fuel they needed to survive. To understand how Japan found itself so catastrophically outmatched, we must go back to the beginning, not to Pearl Harbor, but to the oil fields of Texas and California, to the research laboratories of Standard Oil and DuPont, to decisions made in the 1920s and 1930s that would determine the outcome of battles fought 2 decades later. Aviation gasoline is not simply refined crude oil. It is a precisely engineered chemical compound, blended to exact specifications that determine how an aircraft engine performs. The critical measure is the octane rating, a number that indicates the fuel's resistance to premature detonation, to the phenomenon pilots called knock. When fuel detonates too early in the compression cycle, before the piston reaches top dead center, the resulting shock wave can destroy an engine in seconds. Pistons crack, connecting rods bend, crankshafts shatter. The higher the octane rating, the more compression an engine can use, and compression is the key to power. More compression means more complete combustion, higher cylinder pressures, more force driving the piston down. An engine running on 100-octane fuel can produce significantly more power than the same engine running on 87 octane, simply because it can compress the fuel-air mixture more tightly without detonation. By 1940, the United States had developed the industrial capacity to produce 100-octane aviation gasoline in enormous quantities. This was not an accident. It was the result of deliberate investment, of partnerships between oil companies and the military, of research programs that had begun in the early 1930s. The key breakthrough was the addition of tetraethyl lead, a compound so toxic that workers in early production facilities died from exposure, but so effective at suppressing knock that it transformed aviation engine design overnight. A small amount of tetraethyl lead, measured in cubic centimeters per gallon, could raise a fuel's octane rating by 10 or 15 points. American refineries learned to blend it precisely, to combine it with other additives that further enhanced performance. By 1943, American aircraft were running on fuel rated at 100 octane and above. By 1944, some American fighters were using fuel blended to 115 over 145 performance number, a rating system that indicated the fuel's power output relative to pure iso-octane. Japan had none of this. Japanese refineries in 1941 could produce aviation gasoline rated at approximately 87 octane. This was adequate for the engines Japan was building at the time, the Nakajima Sakai that powered the Zero, the Mitsubishi Kinsei that powered the Betty bomber. These were excellent engines, designed with Japanese fuel limitations in mind. They used lower compression ratios, smaller superchargers, and more conservative timing. They were reliable and efficient. They were also operating at the limit of what Japanese fuel could support. The problem became apparent almost immediately after the war began. Japanese engineers knew that higher-octane fuel existed. They had technical intelligence about American and British aviation gasoline. They understood the theory, but producing it was another matter entirely. Tetraethyl lead required specialized chemical plants, exotic catalysts, precise temperature and pressure controls. Japan had none of these. Worse, the raw materials lead, ethyl bromide, the specific petroleum fractions needed for high-octane base stock were in desperately short supply. Japan had gone to war precisely because it lacked access to these resources. The southern resource area, the oil fields of the Dutch East Indies, the rubber plantations of Malaya, the tin mines of Thailand was supposed to solve this problem. It did not. The oil fields of Borneo and Sumatra produced crude oil, but crude oil is not aviation gasoline. It must be refined, cracked, blended, and treated. Japan captured refineries along with the oil fields, but these facilities had been sabotaged by retreating Dutch and British forces. Rebuilding them took time. Training personnel took time. Shipping the refined product back to Japan through waters increasingly dominated by American submarines took time and tankers that Japan did not have. By 1943, Japanese aviation fuel production was falling behind demand. By 1944, it was in crisis. The engineers at the Nakajima Aircraft Company and the Mitsubishi Heavy Industries research laboratories understood what this meant. They were designing engines for fuel that did not exist, or rather, they were forbidden from designing engines that required fuel Japan could not produce. The Nakajima Homare engine that would power the Ki-84 Hayate was a case study in this dilemma. The Homare was an 18-cylinder radial with a displacement of 36 litres, designed to produce 2,000 horsepower. On paper, it was competitive with anything the Americans were fielding. In practice, it was crippled from birth. To reach its rated power, the Homare needed fuel, with an octane rating of at least 92. Japanese refineries could produce this fuel in limited quantities, but not enough to supply operational squadrons. Frontline units received fuel rated at 87 octane, sometimes lower. At these octane levels, the Homare's automatic boost control a mechanical system that adjusted supercharger output to maintain optimal manifold pressure could not function as designed. Pilots had to manually reduce boost to prevent detonation, which reduced power output by hundreds of horsepower. The engine that was supposed to produce 2,000 horsepower often produced 1,700 or less in combat conditions. Worse, The Homare was notoriously unreliable, even under ideal circumstances. Its complexity, a 2-speed supercharger, direct fuel injection, 18 cylinders each with its own ignition system, meant that maintenance crews, often poorly trained and lacking proper tools and parts, could not keep the engines running. The average time between overhauls for a Homare engine in 1944 was less than 50 hours. The American R2800 could go 400 hours between overhauls, and the R2800 was not even operating at its limit. This was the terrible secret that Japanese engineers began to discover in late 1944, when intelligence reports and captured documents revealed the existence of American war emergency power settings. American fighters, they learned, were not using their engines at full capacity in normal combat. They were holding back, using only military power, a throttle setting that produced maximum continuous horsepower within safe temperature and stress limits. But when a pilot needed everything his engine could give to escape an attacker, to catch a fleeing enemy, to climb out of a dangerous situation, he could push a lever and engage war emergency power. Water methanol injection flooded the intake, cooling the combustion charge and suppressing detonation. The throttle went past the military power stop. The supercharger spun faster. The fuel-air mixture enriched beyond normal limits. The result was a surge of power that seemed almost supernatural. The R2000, 800 inches, a P-47D, already producing 2,000 horsepower at military power, could leap to 2,300 horsepower, or more, at war emergency power. Later variants, with improved superchargers and water injection systems, could exceed 2,500 horsepower. The P-47 Newtons, the long-range escort variant that would dominate the Pacific in 1945, could produce 2,800 horsepower for short bursts. This was not theoretical, it was documented in pilot reports, in captured American technical manuals, in the wreckage of downed aircraft that Japanese engineers picked over with growing disbelief. The mathematics was brutal. A Ki-84 Hayate, Japan's best fighter, might enter combat with an engine producing 1,700 horsepower. Its American opponent could match that at a comfortable cruise setting. At military power, the American had a 300 horsepower advantage. At war emergency power, that advantage became 1,000 horsepower, a 60% superiority that no amount of pilot skill could overcome. Lieutenant Nakajima, floating in the Philippine Sea in February 1945, did not know these numbers. He only knew what he had experienced, the impossible acceleration of the Thunderbolt as it climbed away from his attacks, the relentless pursuits that ground down his energy no matter how he maneuvered. He had been trained to believe that the Japanese spirit could overcome material disadvantage, that the Yamato Damashi, the Japanese fighting spirit, was worth more than industrial capacity. The war had made a mockery of this belief. Spirit did not produce horsepower. Spirit did not refine aviation gasoline. Spirit did not build superchargers. The engineers who recovered the evidence of American fuel technology understood this better than anyone. In laboratories outside Tokyo and Nagoya, they analyzed captured fuel samples, finding octane ratings they had believed impossible, 100, 115, 130. They studied the tetraethyl lead content, calculating the quantities of additive the Americans were using, then calculating how many tons of lead and how many chemical plants would be required to match that production. The numbers were hopeless. Japan's entire tetraethyl lead production capacity in 1944 was less than 2,000 tons per year. The United States was producing over 50,000 tons annually, and still increasing output. There was no way to close the gap. Not in fuel production, not in engine performance, not in the industrial base that made both possible. The engineers wrote their reports and submitted them to their superiors. The reports were classified, suppressed, ignored. What good would it do for pilots to know they were flying aircraft that could never match their opponents? What good would it do for the public to understand that the war was being lost not in battle but in chemistry? And so the Ki 84 seconds and the N1K2S and the Ki 100 seconds kept flying, their pilots brave and often skilled, their engines producing what power they could on fuel that was never good enough. The P-47 seconds and F-6Fs and P-51 seconds kept intercepting them, their pilots sometimes less experienced, their aircraft always better fed. The outcome was never in doubt. But there is more to this story than statistics and specifications. There is the human element, the Japanese engineers who understood what was happening and tried to fight it with the tools they had. The American engineers who built the most powerful piston engines in history. The pilots on both sides who lived and died by decisions made in laboratories and refineries thousands of miles from any battlefield. To understand the full tragedy of Japan's fuel crisis, we must look deeper at the specific moments when Japanese intelligence discovered the truth, at the desperate measures taken to compensate, at the handful of captured aircraft that revealed just how wide the gap had become. The first confirmed intelligence that American fighters were using fuel with octane ratings above 100 came in mid-1943, through a source the Japanese military would never have expected: a shipment of captured British Spitfires. After the fall of Singapore in February 1942, Japanese forces captured several Royal Air Force aircraft intact, including a number of Spitfire Mark Vs that had arrived too late to see combat. These aircraft were shipped back to Japan for technical evaluation, along with drums of fuel and crates of spare parts. Japanese engineers at the Army Air Technical Research Institute at Tachikawa began systematic testing in mid-1942, and what they found troubled them immediately. The Spitfire's Rolls-Royce Merlin engine was rated at over 1,000 horsepower, competitive with Japanese engines of the time, but it achieved this power through different means. The Merlin used higher compression ratios, more aggressive supercharger boost, and more advanced ignition timing than comparable Japanese engines. When Japanese technicians attempted to run the engine on Japanese fuel, the results were catastrophic. Detonation occurred almost immediately at high power settings. Spark plugs fouled, cylinder heads cracked. The engine could not produce anywhere near its rated power. The British fuel captured with the Spitfires was another matter. When the engineers tested it, they found an octane rating of 100. With this fuel, the Merlin ran smoothly at full power. The implications were obvious and alarming. The British, and by extension, the Americans, were operating their aircraft on fuel that Japan could not produce. Every British and American fighter was producing more power than its specifications suggested, because those specifications assumed fuel that Japanese intelligence had not accounted for. This was troubling enough, but the full scope of the problem did not become clear until late 1944, when Japanese forces on Leyte in the Philippines captured several intact American aircraft and, more importantly, several drums of American aviation gasoline. The Battle of Leyte Gulf in October 1944 was the largest naval engagement in history, a desperate Japanese attempt to destroy the American invasion fleet and halt the reconquest of the Philippines. It failed catastrophically. The Imperial Japanese Navy lost 4 aircraft carriers, 3 battleships, and most of its remaining naval aviation capability. But amid the wreckage of this defeat, Japanese ground forces on Leyte itself achieved a small intelligence victory that would haunt their engineers for the remainder of the war. On October 24, 1944, American aircraft from the escort carriers supporting the Leyte landings struck Japanese positions across the island. One of these aircraft, a Grumman F-6F-5 Hellcat from the escort carrier USS Kitkun Bay, was hit by anti-aircraft fire during a strafing run and crash-landed in a rice paddy near the town of Tacloban. The pilot was killed on impact, but the aircraft remained largely intact. More importantly, its drop tank, a disposable external fuel tank carried for extended range, had survived the crash with most of its contents still inside. Japanese army troops secured the wreckage before American forces could recover it. Within days, the aircraft and the fuel were on their way to Japan aboard a transport submarine, one of the few vessels that could still slip through the American submarine blockade, strangling Japanese supply lines. The Hellcat arrived at the Tachikawa research facility in early November. The fuel sample arrived at the Navy Fuel Research Laboratory at Yokosuka a week later. What the engineers found confirmed their worst fears and revealed new dimensions of the problem they had not anticipated. The captured fuel was not simply 100-octane aviation gasoline. It was something more advanced, a blend designated by the Americans as Grade 100/130. The numbers indicated the fuel's performance under two different conditions: 100-octane equivalent at lean mixture settings, 130 at rich mixture with maximum boost. This was fuel specifically engineered for combat, for the moments when a pilot needed every horsepower his engine could produce regardless of fuel economy. The tetraethyl lead content was measured at 4.6 cubic centimeters per gallon, more than double what Japanese refineries could achieve. Additional additives included aromatic compounds that further enhanced knock resistance and combustion efficiency. The fuel was, in the words of one Japanese engineer's report, a product of industrial chemistry beyond our current capabilities. The Hellcat itself told a similar story. Its Pratt & Whitney R2-80010W engine, the W designating water injection capability, was removed and subjected to exhaustive testing. Japanese engineers measured compression ratios, supercharger gear ratios, valve timing, and ignition. Advance. Every specification confirmed that the engine was designed to operate on fuel Japan could not produce. When they attempted to run the engine on Japanese 91-octane fuel, the best available power output dropped by nearly 20%. The engine ran rough, detonation limiting boost pressure well below the design maximum. Only when they used the captured American fuel could the engine produce its rated power, and only then did the water injection system reveal its true purpose. Water injection was not a new concept. Japanese engineers had experimented with it as early as 1942. The principle was simple: inject a fine mist of water, or water mixed with methanol, into the intake manifold. The water absorbed heat as it evaporated, cooling the intake charge and reducing the tendency toward detonation. This allowed higher boost pressures and more aggressive ignition timing without engine damage. In theory, any engine could benefit from water injection. In practice, the benefits depended entirely on the base fuel quality. On Japanese fuel, water injection provided modest gains, perhaps 50 or 100 additional horsepower, with significant reliability penalties. The water had to be carefully metered to avoid washing lubricating oil from cylinder walls or contaminating the combustion process. Japanese water injection systems were crude, unreliable, and seldom used in combat. On American fuel, water injection was transformative. The already high octane rating meant that engines could run higher boost pressures than Japanese engines at baseline. Water injection pushed this advantage further, suppressing detonation even at manifold pressures that would have destroyed a Japanese engine instantly. The R2000, 800 inches the Hellcat, could produce 2,000 horsepower at military power on American fuel without water injection. With water injection at war emergency power, it produced over 2,100 horsepower. The penalty was increased: fuel consumption and slightly higher engine wear, but American industry could afford both. The engineers at Yokosuka calculated what these numbers meant in combat. A Japanese pilot in an A6M50, the most numerous Japanese fighter in late 1944, had an engine producing approximately 1,100 horsepower. His opponent in a Hellcat had nearly twice that power available at war emergency power. The Zero was lighter, more maneuverable at low speeds, and could turn inside the American fighter. None of this mattered. The Hellcat pilot controlled the engagement. He could choose when to attack and when to disengage. He could convert altitude to speed and speed back to altitude faster than the Zero could respond. If the Zero pilot made a mistake, if he bled too much energy in a turn, if he let his speed drop too low, the Hellcat would be on him before he could recover. And if the Zero pilot gained a momentary advantage, the Hellcat could simply run away, using its superior power to open distance until it could reset the engagement on favorable terms. This was the reality that Japanese fighter pilots faced every day by late 1944, and it was about to get worse. In early December 1944, intelligence reports reached Tokyo describing a new American fighter operating from bases on Saipan and Guam. It was not the Hellcat or the Corsair that Japanese pilots had learned to fear. It was something larger, heavier, and somehow faster than either. Pilots who survived encounters described an aircraft that seemed to ignore the normal constraints of physics, a machine that could dive at speeds that would tear the wings off a zero, then pull out and climb at angles that should have been impossible for something so massive. The reports called it the P-47 Newtons, the newest variant of the Republic Thunderbolt, and they described it in terms that bordered on disbelief. The P-47 was not a new aircraft. Earlier variants had served in the Fashion, European theatre since 1943, earning a reputation as a rugged, heavily armed fighter bomber that could absorb tremendous punishment and still return home. But those early Thunderbolts had limitations. Their range was short, their climb rate mediocre, their performance at altitude merely adequate. The P-47 Newtons was something different, a complete redesign that addressed every weakness while amplifying every strength. The N model carried internal fuel tanks that more than doubled the aircraft's range, allowing it to escort B-29 bombers from the Marianas to targets over Japan and back. Its wings were redesigned with squared-off tips that improved roll rate and reduced drag. Its engine, the Pratt & Whitney R280057 or -77, incorporated every advancement American engineers had developed over 3 years of war. With water injection and war emergency power, these engines produced 2,800 horsepower, nearly 3 times the power of a Zero, nearly 50% more than Japan's best fighter, the Ki-84 Hayate. The first P-47Ns arrived on Saipan in January 1945. Within weeks, they were flying long-range escort missions over Japan, and Japanese pilots were dying in numbers that shocked even the most pessimistic commanders. The American pilots were not necessarily more skilled. Many were fresh from training, with a fraction of the flight hours their Japanese opponents had accumulated. But skill was no longer decisive. The P-47 Newtons was so fast, so powerful, so capable of dictating the terms of every engagement that pilot skill became secondary to aircraft performance. A novice in a Thunderbolt could defeat an ace in a Hayate simply by using his power advantage to maintain separation, to choose his attack angles, to escape when threatened, and return when opportunity arose. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content, like this. Japanese engineers studying the intelligence reports understood what they were reading. The P-47 Newtons was not merely a superior aircraft, it was an aircraft that operated in a different performance envelope entirely. Its power-to-weight ratio at war emergency power exceeded anything Japan could field. Its ability to generate and retain energy to climb, dive, and accelerate made Japanese fighters obsolete, regardless of their handling qualities or pilot training. And the source of this superiority was not primarily aerodynamic or structural. It was chemical. It was fuel. By February 1945, the Navy Fuel Research Laboratory had compiled a comprehensive report on American aviation gasoline production. The findings were devastating. American refineries were producing over 500,000 barrels of 100-octane aviation fuel per month, more than Japan's total aviation fuel production of all grades. The American supply of tetraethyl lead was essentially unlimited, with domestic production supplemented by imports from Mexico and South America. American chemical engineers had developed catalytic cracking processes that converted low-grade petroleum fractions into high-octane blending stock with efficiency that Japanese technology could not approach. The report estimated that even if Japan somehow obtained the necessary raw materials and chemical plants, it would take 3 to 5 years to develop comparable production capability. Japan did not have 3 years. It did not last 3 months. The engineers who wrote the report understood this. They included recommendations, desperate measures that might partially offset the fuel disadvantage. Reduced compression ratios in new engine designs, revised ignition timing maps that sacrificed power for reliability, water injection systems using lower purity methanol that was easier to produce, changes to pilot training that emphasized energy management and disengagement tactics over the tekele, aggressive dogfighting that Japanese doctrine had always favored. None of these measures could close the gap. They could only narrow it slightly, buying time that Japan no longer had. Some engineers proposed more radical solutions. One group at Mitsubishi suggested developing engines that could run on lower octane fuel by using variable compression, a mechanical system that would adjust the compression ratio based on fuel quality and power demand. The concept was technically feasible, but would require years of development and testing. Another group proposed alcohol-based fuels, using Japan's abundant rice and sugar production to create ethanol that could be blended with gasoline. This was actually implemented on a small scale, but the results were disappointing. Alcohol-gasoline blends produced less energy per volume than pure gasoline, reducing range at a time when range was already critical. The most desperate proposal came from a young engineer named Takeo Doi, who would later become famous for his work on Japan's post-war aircraft industry. Doi suggested abandoning piston engines entirely and accelerating development of jet and rocket propulsion. Jet engines, he argued, did not care about octane ratings. They burned kerosene, which Japan could produce in adequate quantities. A jet fighter would not need to worry about detonation, about compression ratios, about all the constraints that were strangling Japanese piston engine development. It would compete with American aircraft on different terms that might favor Japanese engineering strengths. Doi was right, and his proposal was rejected. Japan did develop jet aircraft, the Nakajima Kikka and the Yokosuka Oka among them, but too late, in too few numbers, with too many technical problems. The first Kikka flew on August 7, 1945, one day after Hiroshima. The jet age would come, but not in time to save Japan. In the meantime, Japanese pilots continued to fly their piston engine, fighters against American opponents who held every material advantage. Some Japanese pilots achieved remarkable results through skill, courage, and tactical innovation. Warrant Officer Naoshi Kano of the 343rd Naval Air Group claimed over 20 victories in the war's final months, flying an N-1K-2J Shidenkai that was Japan's best naval interceptor. Lieutenant Takashi Oshibuchi of the 47th Sentai became an ace several times over in his Ki-84 Hayate, using his experience and energy management skills to survive encounters that killed less capable pilots. These men were exceptional, and their achievements only underscored the futility of Japan's position. For every Kano or Oshibuchi, dozens of Japanese pilots died in their first or second combat mission, overwhelmed by American aircraft they could not match and American tactics they could not counter. The mathematics were pitiless. In January 1945, Japan lost over 500 aircraft in combat and operational accidents. It produced fewer than 2,000 to replace them, and many of these were trainers and transports rather than combat aircraft. The United States, by contrast, was producing over 7,000 aircraft per month. American losses in the Pacific were replaced immediately, often with improved variants. Japanese losses were replaced slowly, with aircraft that were frequently inferior to the ones they replaced because the engines were derated for lower quality fuel and the pilots had less training. By spring of 1945, many Japanese units had simply ceased to exist as effective fighting forces. The fuel shortage had become so acute that training was curtailed to almost nothing. Pilots arrived at operational squadrons with as few as 100 total flight hours, compared to over 300 hours for American pilots before they reached combat units. These novice Japanese pilots were flying aircraft with unreliable engines, using fuel that prevented those engines from producing their designed power against American opponents who had better aircraft, better fuel, better training, and overwhelming numbers. The kamikaze campaign that dominated Japan's air war in the final months was, in part, a response to this hopeless situation. If Japanese pilots could not survive long enough to become skilled, if Japanese aircraft could not match American performance in conventional combat, then perhaps deliberate self-sacrifice could achieve what conventional tactics could not. The logic was grim but coherent. A kamikaze pilot needed only enough skill to take off, navigate to the target area, and dive into an American ship. He did not need to dogfight, to evade interceptors, to land safely. His aircraft did not need to produce maximum power or operate reliably for more than a single mission. The fuel shortage that crippled conventional operations mattered less when the operation was one way by design. The kamikazes achieved results. They sank or damaged dozens of American ships and killed thousands of sailors, but they could not change the outcome of the war. And they consumed pilots and aircraft that Japan could not replace, accelerating the collapse of Japanese air power rather than reversing it. On the morning of May 25, 1945, a formation of P-47NS from the 318th Fighter Group took off from Ie Shima, a small island off the coast of Okinawa. Their mission was to escort B-29 bombers attacking the industrial city of Nagoya on the Japanese mainland. It was a long mission, over 1,500 miles round trip, but the N-model Thunderbolts had the range. Barely. They would arrive over Japan with enough fuel for perhaps 20 minutes of combat before they had to turn for home. The American pilots were not worried. They had flown this route before, and they knew what to expect. Japanese interceptors would rise to meet them, but the interceptions had become increasingly disorganized as Japanese fuel, supplies dwindled and experienced pilots died. Sometimes the Japanese fighters did not appear at all. When they did, they were often cautious, making single passes before diving away, rather than pressing sustained attacks that would drain their fuel and expose them to American counterattacks. Over Nagoya, the expected interception materialized a mixed group of Ki-84 Heights and Ki-61 Hiens from the 56th Sentai, one of the few Japanese Army fighter units still capable of sustained operations. The Japanese pilots were experienced, several of them aces with years of combat experience. Their aircraft were painted in the dark green camouflage that had replaced the earlier light grey schemes as Japanese control of the air disappeared. They came in from above, diving through the bomber formation, targeting the B-29 seconds with cannon and machine gun fire. The P-47 seconds responded according to their training. They did not try to match the Japanese fighters in tight maneuvering combat. Instead, they used their power advantage to maintain energy, to stay fast, to take slashing attacks, and then extend away before the Japanese could respond. When a Ki-84 got on a Thunderbolt's tail, the American pilot did not turn and fight. He pushed his throttle past the war emergency power stop, felt the surge as water injection activated, and simply accelerated away. The Ki-84 could not follow. Its engine was producing perhaps 1,600 horsepower on the 91-octane fuel that was the best available to frontline units. The P-47's engine was producing over 2,600 horsepower. Within seconds, the American was out of range, climbing back to altitude to reset the engagement. The combat lasted less than 10 minutes. 4 Japanese fighters were shot down. 1 P-47 was damaged but made it back to Ie Shima. The B-29 seconds completed their bomb run and turned for home. It was a minor engagement, one of hundreds that occurred over Japan in the war's final months. It was also a perfect illustration of everything that had gone wrong for Japan. The Japanese pilots who survived that engagement landed at their base with nearly empty fuel tanks, their engines running rough from the detonation damage that accumulated with every combat mission. They reported their losses, received replacement aircraft that would take weeks to arrive, and prepared for the next mission knowing that nothing had changed. Their enemies would still be faster, still more powerful, still able to dictate the terms of every fight. The fuel that might have made a difference did not exist, and never would. In Tokyo, the engineers who understood the fuel crisis continued their work, though by spring of 1945 it was clear that nothing they did would matter. The Navy Fuel Research Laboratory was bombed in March, destroying months of research and killing several engineers who had written the reports on American fuel production. The Tachikawa Army Air Technical Research Institute was hit in April, badly damaging the facilities where the captured Hellcat had been tested. The infrastructure of Japanese aviation research was being systematically eliminated, along with the infrastructure of Japanese industry. Fuel production, already inadequate, collapsed almost entirely as refineries were destroyed and transportation networks severed. By June 1945, many Japanese aircraft were grounded permanently. There was no fuel to fly them, no parts to maintain them, no pilots trained to fly them. The remnants of Japanese air power were husbanded for the expected American invasion of the home islands, a final kamikaze campaign that was supposed to inflict such casualties on the invasion fleet that the Americans would negotiate rather than fight. Whether this strategy would have worked became irrelevant on August 6th, when the first atomic bomb fell on Hiroshima. Japan surrendered on August 15th, 1945. The formal ceremony took place on September 2nd, aboard the battleship USS Missouri in Tokyo Bay. Among the observers was a group of American technical intelligence officers whose job was to evaluate captured Japanese equipment and interview Japanese engineers. Over the following months, these officers compiled detailed reports on Japanese aviation technology engines, airframes, weapons, fuel. They interviewed the surviving engineers from Nakajima and Mitsubishi, from the Army and Navy research institutes. They asked about every aspect of Japanese aircraft development, including the fuel problem that had crippled Japanese engine performance throughout the war. The Japanese engineers were remarkably candid. They had nothing left to hide, and many of them were relieved to finally explain what had gone wrong. They described the pre-war decisions that had left Japan dependent on imported fuel technology. They described the failed attempts to develop domestic tetraethyl lead production. They described the compromises forced on engine designers who had to optimize for fuel that barely existed. They described watching their best aircraft fall from the sky because they could not be fed the gasoline they needed. One engineer, his name was not recorded in the American report, described examining the captured Hellcat engine at Tachikawa in late 1944. He knew immediately what he was looking at. He had understood the compression ratios, the boost pressures, the ignition timing curves. He had understood that this engine was designed for fuel Japan could not produce and would never produce. He had understood that all of Japan's efforts to build better fighters, the Ki-84, the N-1K2, the Ki-100, were ultimately futile because the engines could never produce their designed power. He had written a report explaining all of this, recommending fundamental changes to Japanese engine development strategy. The report had been filed and forgotten. Nothing had changed. The engineer was asked what Japan should have done differently. He thought for a long moment before answering. "We should have understood sooner that this was an industrial war," he said, according to the American transcript. "We believed that spirit and skill could overcome material disadvantages. This was a comforting belief. It was also a fatal one. The Americans did not defeat us with courage or tactics. They defeated us with chemistry and manufacturing. They built engines that were designed for fuel we could not produce, and then they produced that fuel in quantities we could not imagine. Every battle we fought at a disadvantage that had nothing to do with the men or machines actually present. The disadvantage was created in refineries and chemical plants, years before the fighting began. By the time we understood this, it was too late to change it. Perhaps it was always too late. The American officers compiled their report and moved on to other tasks. The occupation of Japan continued. The engineers who had built Japanese aircraft during the war went on to other careers, some in the aircraft industry that would eventually produce the Shinkansen bullet train and the Honda Civic, others in fields unrelated to their wartime work. The P-47 seconds and Hellcats and Corsairs were scrapped or sold to foreign air forces. The Heights and Shidenkais and Hiens were almost entirely destroyed, only a handful surviving in museums. The fuel that had determined the outcome of so many air battles was simply consumed, burned in engines that would never fly in combat again. But the lesson remained, the lesson that Lieutenant Tadashi Nakajima learned floating in the Philippine Sea in February 1945, that the engineers at Tachikawa learned examining the captured Hellcat, that the entire Japanese military establishment learned too late to do anything about it. Wars are not won only by brave pilots and brilliant commanders. They are won by industrial capacity, by logistics, by the ability to produce vast quantities of precisely engineered material and deliver it where it is needed. Japan went to war believing that superior training and fighting spirit could overcome American industrial strength. This belief was tested in every air battle over the Pacific, and it failed every time. The American pilot in his Thunderbolt did not need to be braver or more skilled than his Japanese opponent. He only needed to push a lever and feel his engine surge with power that the Japanese pilot could not match. The P-47 Thunderbolt that produced 2,800 horsepower with war emergency power was not a miracle of engineering, though it was an impressive achievement. It was the product of a system of research, production, logistics, and training that worked together to create capabilities that no single component could achieve alone. The high-octane fuel that unlocked the engine's power was part of this system. So were the refineries that produced the fuel, the tankers that delivered it, the chemical plants that manufactured the tetraethyl lead, the research laboratories that developed the additives. The Japanese engineers who discovered the American octane booster were not just discovering a chemical compound. They were discovering the material reality of American power, the ability to coordinate vast industrial resources toward a single purpose and sustain that effort across years of global war. Japan could not match this system. No amount of courage, skill, or determination could substitute for it. The Japanese pilots who flew against American fighters in 1944 and 1945 were not defeated because they were inferior aviators. Many of them were superb, with thousands of hours of flight time and years of combat experience. They were defeated because they were flying aircraft that could not be fueled properly, maintained properly, or replaced when lost. They were defeated by the mathematics of industrial warfare, by octane, ratings and production figures and supply chains. They were defeated by chemistry. Lieutenant Nakajima survived the war. He was recovered by that Japanese patrol boat, spent several weeks in a military hospital recovering from exposure and his injuries, and was reassigned to a training unit where he taught new pilots the skills they would need to survive, skills that became increasingly irrelevant as Japanese fuel supplies collapsed and flight training virtually ceased. He never flew in combat again. After the war, he returned to civilian life, like millions of other Japanese veterans. He rarely spoke about his experiences. When he did, he focused not on the fear or the violence, but on the frustration of flying an aircraft that should have been competitive but was not, of doing everything right and still being unable to escape the American on his tail. It was not a fair fight, he told an interviewer decades later. I do not mean this as an excuse. I mean it as a fact. Their engines were stronger because their fuel was better. We knew this by the end, all of us knew it. But knowing did not help. We flew anyway because there was nothing else to do. The story of Japanese engineers discovering American octane boosters is, in the end, a story about the limits of human agency in industrial warfare. The Japanese pilots were not lacking in skill or courage. The Japanese engineers were not lacking in intelligence or dedication. They were operating within constraints that doomed their efforts before they began constraints imposed by geography, by resources, by pre-war decisions that could not be reversed once the fighting started. The Americans who defeated them were not necessarily braver or smarter. They were simply better supplied, their engines fed with fuel that Japanese refineries could not produce, their aircraft rolling off assembly lines that Japanese industry could not match. This is not a comfortable lesson. It does not celebrate individual heroism or brilliant strategy. It celebrates logistics, chemistry, and industrial planning. But it is the truth, and the Japanese engineers who discovered it in the final months of the war understood it better than anyone. The cylinder head temperature gauge in Lieutenant Nakajima's Hayate climbed past the red line because his engine was straining to produce power it was never designed to produce on fuel that was never good enough. The P-47 behind him pulled closer because its engine was loafing at settings that would have destroyed the Hayate, with hundreds of horsepower still in reserve if the American pilot needed them. The war ended the way it did because one side had learned to turn petroleum into power more efficiently than the other. Every death in every air battle over the Pacific was, in some sense, determined by octane ratings, decided in laboratories years before. The Japanese engineers who discovered this truth could do nothing to change it. They could only document it, explain it, and hope that someone would learn from it. That is the legacy of the American octane booster, not just a chemical additive, but a symbol of the industrial capacity that won the war. The P-47 that produced 2,800 horsepower was the culmination of that capacity, an aircraft that could not have existed without the fuel to feed it, the factories to build it, the training infrastructure to crew it, and the logistics network to supply it. Japan had none of these things in adequate quantity. Japan lost. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.